Hello, everyone. Good afternoon. My name is Prasanna, and this is Hila from Nuvoton. We will be talking about the Caliptra and Nuvoton Arbel tip and the root of trust solution that's available as part of it. There we go.
Okay, so both Caliptra and the TIP are integrated root of trust. So what we are going to talk about today is, first of all, provide motivation for integrating the root of trust into the BMC. Then we're going to talk features and functionalities, show you a few of the services, explain a little bit about our future plans, and then Prasanna will take you into a deep dive into the AMI Tectagon orchestration of the integrated root of trust. So let's start with motivation. The first motivation for integrating the root of trust into the BMC, with the BMC into the same solution, is to be able to avoid any kind of attacks that are related to substitution of device or interposing. I guess it's pretty much self-explanatory. If it's internal, then nothing can come in between. A second reason, if the root of trust is integrated into our solution, that means that it can also add configuration into its measurements. I mean, it doesn't only measure the image and the subcontent of the image, it can also measure the state of the BMC. Configuration parameters like life cycle or debug state or security state, all that is part of our fuse array, for example. And if the root of trust is integrated, it has full access to it, it can measure it. Next, there are stages in the lifetime of the BMC that are a little bit more critical than others. For example, firmware update or recovery. Now, generally, the BMC would have to check on the health of the root of trust, make sure that's in a healthy state before using it. In our case, it doesn't have to because it's integrated. Single pass. Now, with an integrated root of trust, you can provide one single report, a single pass, starting with the root of trust all the way to the BMC and even to some external devices. And you give that report in one single answer in a single pass, which is probably safer, but also a lot more efficient. Next, there are services. Okay, so basically you have the root of trust alive all the time when it's integrated, so you can use it throughout the process of the BMC. If we take, for example, a process like the firmware TPM, which is alive on the BMC, but it's endorsed by the root of trust, and the root of trust can take active part in its operation. Refresh the chain whenever it's necessary. Runtime authentication of the RAM. Root of trust is alive. It can constantly authenticate critical portions of the RAM, make sure that no one hassled with our Linux kernel, for example. And there's also a case of root of trust providing services to the BMC, security services. If the BMC requires signature or authentication, or even encrypt or decrypt of data on the memory, it can contact the root of trust and ask the root of trust to perform that for him. Or it can do it using its own cryptographic engine, but the keys and the configuration is controlled by the root of trust. Root of trust is used as a vault, so that information is not exposed to the BMC. And, oh, no, please, now. The last element actually is something that can be done with a discrete root of trust as well, but then you are limited by the speed of the bus. If it's an integrated solution, bus is no longer a limitation. It really increases performance, and that's also a good thing. Okay, let's do an overview of the hardware and the features and the requirements from a root of trust solution. So ignore the dimensions. We are giving way too much respect to the root of trust in this diagram. So we have the BMC component, and the BMC is running OpenBMC, which is a non-secured applications, but it also runs secured application because we support ARM trusted firmware, and we have Trust Zone, which is a hardware isolation layer. The other big shape here is the root of trust. Standalone encapsulated solution, a silicon that doesn't need anything from the environment, and when it needs something, it takes it. It has its own ROM, its own internal RAM, accessed only by the tip. No one else can access that. It has its own security accelerators and a few peripherals that we thought might be handy for it, like GPIO, I2C, UART. Between the two of them, the BMC and the root of trust, there's a fabric. And that fabric is very critical because it can also control the access. For example, you can have a peripheral dedicated to tip or open to everyone, OpenBMC, for example, or open to tip and to the BMC running secure mode only. Now that interconnect fabric is also controlled by the tip. So it's basically tip setting the tone, telling which peripheral can be accessed or memory can be accessed by which component. Between the CPU and the BMC, there are basically two means of communication. It's not exactly that. There is one mean of communication, and that's the mailbox. There's a mailbox. It's like a dual port register with interrupt, like a doorbell, and that's the only way to get in touch with the security processor. It doesn't have an interface other than that. The AES that you see over there is a nice example of how the root of trust can assist the BMC in performing cryptographic services. Now, the BMC has its own AES engine. It can use that for encryption or decryption, sign or verify, whatever it likes, but the keys and the configurations can be controlled by the root of trust. So basically, BMC is left with all the hard labor, and all the good stuff is kept inside the root of trust, and the BMC has no way to access that. On the right side, you see the memories. Now, external memories are a big problem. There are external memories, so that's what makes them so problematic. So in case of the DRAM, our memory controller has a similar interface as the fabric. You can define who has access to it and who doesn't. It can be tip, it can be tip in secured mode, it can be anyone. Same with the SPI. And if you need encryption, decryption on any of those memory, then that's fine. The root of trust will take care of that for you. And as always, the keys are private to the root of trust. BMC is never exposed to the keys. So basically what we have here is a root of trust that through a fabric and memory controller configuration controls all the access modes. And it's through the lifespan of the BMC, not just an initial state. He's afraid of me now, I think. Okay, this is basically same information shaped a little bit different. I would like you to pay attention to the things that weren't very highlighted in the previous one. One of them is the flash monitoring. The root of trust has an ability to monitor the external flash and prevent for execution of commands based on a predefined list, of course. It can prevent changes, erase of the entire SPI device or just regions of it based on the configuration. In addition to that, it also has monitoring module, flash monitoring, which can constantly compare between the DRAM and whatever data is on the flash, making sure that the data on the DRAM wasn't changed. So that's what I talked about when I said that the integrated root of trust can constantly monitor that no one is messing with a kernel. That's the one. Is there anything else I want to show here? No, I think so. Basically, it's very, very much like the previous slide. Oh, it's faster than I. Services, let's talk about services. So the first service that root of trust has to provide is actually through the stage of the manufacturing, the provisioning. While during manufacturing, each one of our samples gets its own unique identity. From that identity, we generate the DME, device manufacturing identity. We harvest that and we provide our customers with a list of the DMEs so they can verify every time that each sample is located exactly where it's supposed to be. From the DME, we generate the dice identity and the dice key. And from that dice key, we can generate as many alias keys as we want, so that the BMC can use them or the TIP can use them for any kind of security purpose that they have. The next one, most important and also not a very new thing, the secure boot and the measurements, of course. I would like to say only that in the case of an integrated root of trust, as I said before, you can measure things that you couldn't measure with a discrete device, and that's the internal state of the processor, including data from the fuse array and stuff like that. Lifecycle management, also a service provided by the integrated root of trust. Life cycles can be development or production, which are mutually exclusive. You can go from one to another, but there is RMA and there is end of life, and it's the integrated root of trust in charge of changing the state. Secure firmware update and secure firmware recovery, two tasks that also I would say managed and run by the integrated root of trust, and that's thanks to the fact that it's constantly alive. So it can be used to lead those tasks. It can control the secure firmware update of itself, the BMC, external components like the BIOS flash, and a coprocessor, which I haven't mentioned because it's not related to the topic here. Other services. So as I said, the integrated root of trust can be used as a vault to store keys, whether it's in his memory or as it can also be stored on secured memory that can be accessed only by the TIP, in the TIP internal RAM, in the flash after it's being encrypted. There are many ways, but the main idea here that the secrets are never leaving the integrated root of trust, and the BMC has access to them only when it wants the job to be done. It's never ever kept outside the reach of the TIP and the TIP only. The TIP can provide cryptographic services, whether the BMC is asking the TIP to do the cryptographic services for it, or the BMC is doing its own cryptographic services with its own engines, but configuration and keys come from the TIP directly without BMC ever being exposed to them. We can do constant measurements of the Linux kernel. We do the endorsement and the refreshment of the keys for the firmware TPM, which is running on the BMC as part of an OpenBMC solution. And the integrated root of trust can also encrypt and decrypt the non-volatile memory. So our firmware TPM solution would have a non-volatile memory, which TPM sometimes needs. As for firmware, well, Nuvoton implemented together with Microsoft DICE firmware based on Microsoft Cerberus. AMI are building Tectagon, and soon there's going to be a deep dive into that, which Presanna will lead. Okay, past, present and future. So as I said before, we are already in production with our BEL, the NPCM 8M and X. Our solution includes an integrated root of trust, which is called the TIP. Version A2 is FIPS compliant and OCP safe. Version A3, in which we added LMS support, well, it's not certified yet. We have already submitted all the documentation. We are waiting for the approval to come. So our next generation, the Tavo, is going to be Caliptra. Okay, so next generation Tavo is going to be Caliptra. We are moving towards integrating the Caliptra instead of the current solution of the A2 and the A3 that have a TIP embedded inside. And the reasons for the change are both marketing and technical. We believe that the industry is going towards unification of the root of trust, Caliptra, for example, and we are part of the industry, so we're moving along. It's actually basically taking the proven technology of the TIP and moving forward with the same technology. We're not changing our minds, we're just replacing the processor. Now, Caliptra is completely open source. It has a full hardware and software stack that has to be integrated into your solution, but basically ROM and firmware and APIs and a very large firmware stack, you get it as part of the solution. And I would say that this is the most important thing. Is the most important reason to move to Caliptra is the power of the community. We are all here attending an open BMC conference, which means that we believe in the power of the community, especially in the case of security. You should probably have as many people as possible joining in hands, trying to identify the risks, mitigate the solutions, find a solution. And what we also believe that will be in the future is that Caliptra will be integrated into more modules. And it will be very good if all these modules have the same API, the same methods, the same response, the same trust level. So this is why we are moving into Caliptra in the next generation. And I believe.
Thank you. So Hila had just talked about what are the functionalities of the root of trust embedded into the BMC silicon SoC. What it does is it provides you a root of trust, a source of truth, but it does not provide without the firmware. It's just a module. I mean, you need orchestration firmware that actually exercises the capabilities available in the in the silicon to provide those security services. So this is where the root of trust orchestration firmware comes in. So as part of a root of trust orchestration, you get the firmware authentication and establishing of the integrity of the firmware, runtime monitoring like Hila had indicated, and protection as part of spy filtering and SMBus filtering. You have recovery and resiliency. So basically, in the event firmware is compromised, you need to be able to recover it. And you have the lifecycle management. So you have the secure update, the key management, and other OTP enablement, device ownership transfers. All these need to be done. So as part of the Arbel CPU, SoC, you have three different layers. The bottom layer is actually the hardware. It provides the device identity, the cryptographic engine, the key storage, all the necessities that are required to implement an orchestration firmware. On top of that, we have the middle layer, which is the platform root of trust, which is where all these features that we were saying that are required to protect your platform comes into play. And then on top of that is your firmware, the OpenBMC firmware or any proprietary firmware, BMC stack that may be implemented. Tectagon is AMI's solution at providing a platform root of trust orchestration firmware. Here we will be able to provide the different functionalities that are required. It runs on top of the TIP, and it provides you secure firmware update, authentication of firmware authentication and verification. It has active recovery capabilities, secure firmware update, and it provides you observation via logging and key management capabilities. And we are also engaging with Nuvoton in adding PQC capabilities with LMS cryptographic engine. So how does it look in the SPY? So in the SPI, you have the TIP boot ROM that is available. Then we have the Tectagon firmware that is getting loaded by the boot ROM. And the Tectagon firmware then validates the BMC firmware stack and based on manifest. And then after a verification, successful verification, it loads the firmware into memory and for execution. This is what I'm showing here. What is shown here is the dual SPI layout. It can also be implemented in a single SPI, but this is this is the dual SPI layout. The secondary SPI basically has the recovery image, the PFM recovery manifest, and the staging area if required. So the updates are done using the staging region. So whenever the platform is requiring an update, we have the BMC UI or Redfish APIs flash the firmware into the staging region and then let the TIP know that there has been an update happen, after which TIP will verify and perform the updates.
Now we have the two multi-stage secure boots, which are probably more the same than different. So in our case, we start by root of trust, getting out of reset. BMC is still in reset. There's no way that the root of trust is in reset and BMC is alive. The opposite does happen. So first we start with the ROM, which is FIPS compliant and OCP safe also. And the ROM code does the preliminary authentication based on keys that are stored in its fuse array of the first. So once a chip is in secured mode, it can only run secured firmware. I mean, there's no way of running firmware that is non-secured. Next, it loads the first layer of the DICE firmware, which we call L0. L0 loads L1. And at that point, we have the integrated root of trust running its firmware completely. And it starts with the authentication of the BMC side of the image. So first there's the boot block, which is loaded from authenticated, loaded to the internal flash of the BMC. And the boot block is in charge of hardware configuration, including memory controller. Once boot block is done, we have the entire DDR available, and the root of trust continues to the next components, which are ARM trusted firmware. We have the monitor firmware and OPTI. Again, it copies, authenticates, and then last is the U-boot, and the BMC start executing all the threes. At that stage, by the way, if authentication was completed, it stores a recovery image of what it had already authenticated. And from that moment on, actually, the BMC is running. It can run non-secure application. It can run secured applications like firmware TPM. Firmware TPM can do security tasks when it's running in secured mode, etc.
So this is a representation of the same thing that Hila said, but where each of the phases are going to be executed from. So the TIP ROM, the secure boot, DICE initialization or setting up of the certificates, then Tectagon, and the T-1 verification. All this is happening in the TIP, which is a Cortex M4 CPU. Once it has been released, once it has verified that the firmware is authenticated and it releases it, the rest of the system is taken over by the A35 SoC, ARM SoC. This is where it loads the boot block, the BL31 OPTI on the U-boot. And once U-boot is loaded, it enables the SPI filtering and starts executing the Linux kernel, and the BMC is up and running. So This slide basically talks about what is happening as part of the the root of trust orchestration. So the root of trust orchestration has different stages: verify, recovery, update. It goes into hold. It has to do a recovery update. It has to do PROT updates. It has to do I2C filtering, SPI filtering. So this here, if you see in the verify state, it basically attempts to verify the the firmware in the SPI. Once it is verified successful, it releases, it sets the SPI filtering and it releases the firmware for boot. But if it doesn't verify successful, authenticate as successful, then it has to move into the recovery state, perform the recovery operation, and then it has to re-verify that whatever it has recovered is correct, and then release it to boot. In the event, even the recovery is failed, it has to go into the lockdown state. So this is not a one-time operation. This has to happen every time a platform is powered on, reset, or an update happens. This state mission has to be followed throughout the life cycle of the platform. So today we talked about, what we are doing today is based on the TIP firmware, TIP implementation on the Nuvoton SoC. But as Hila had mentioned, future is towards Caliptra. What we are going to be doing, the industry is moving towards implementing Caliptra in their SoCs. So as part of AMI's Tectagon roadmap, we do have plan on supporting Caliptra, where we plan on using the orchestration layers to add value on top of what is available with Caliptra and ensure that the industry is protected with enhanced security mechanisms. So we plan on working with all Caliptra-enabled SoCs in the future, like Terror, and implement our solution on top of it. So what are the key takeaways? So Arbel TIP is basically a silicon root of trust. Tectagon provides the orchestration layer on top of it. It does the platform, the life cycle of this thing, verify, decide if it's valid, and release the A535 cores. It provides a continuous life cycle for the firmware that is being executed. And we are also planning on supporting Caliptra 2.1 MCU in all the new silicons that will be supporting those.
So the last slide here is an example of an application. And I think what you got from these two sections is that the integrated root of trust is just the hardware. It's the vehicle. It has requirements. It has to meet specific rules. But once you have it, you can go into very different directions. And I think you could very easily say that there's a few things that are different between what I described and what Tectagon has implemented. It's just as good, but it's a different way of using the same integrated root of trust. I suppose that would also happen with Caliptra. We're going to see a lot of solution based on one specific silicon. Now, the case of the FTPM is interesting because it actually, I think, the only case that really combines OpenBMC and the integrated root of trust, and OpenBMC is the reason why we all gathered here in this room. So we decided that we're going to talk about it a little bit. So the security, the trust, the power is in the hands of the integrated root of trust. It has its own identity. It was given to it during the provisioning state. It has the DME, it has the dice. And from the dice key, you can generate any alias key that you like. And those alias keys are used to give that gift of security to other components in the system. And the system that I decided to talk about is the FTPM. It could be any kind of secured application running. FTPM is not ours, it's open source. We integrated it into our system, but that's just it, integration. The endorsement key, the key that actually the TPM uses to identify itself in the real world, it gets it from his host. Now we are the host. We are generating the EK for the TPM, and we're doing it based on the DICE alias key. And from that moment on, our TPM can identify itself, and it can generate the AIK, which are the keys, the key pairs that the TPM can use for its own security services. So what you see here is a flow in which the trust comes from the integrated root of trust. The TPM was able to get an identity from the integrated root of trust, but once it has that identity, it can use it to perform its own standalone security task. It can sign and endorse itself and present itself based on the identity that it got from the root of trust. Now, since the root of trust is always alive, the process can be replaced, can be refreshed. I mean, there's no problem. You can just generate new keys in the very same method that you did, except, of course, the DME and the DICE, which are embedded inside the root of trust. That's its identity. The advantage that we get by having the FTPM, in addition to the fact that I found something to talk about in an OpenBMC conference, is the fact that we can enjoy what we call the TCG log now. TCG has been there for a lot more years than security in the BMC. And TCG log is a very nice way of packaging the information that you want to log out, the security information that you log out, which starts all the way from the root of trust and ends in the smallest device that you are testing during or doing the measurements. But it's also ongoing. You can do ongoing measurements and still use the TCG log as a, I would say, international format of outputting your information, outputting your report. And that comes for free just by integrating the firmware TPM. So the root of trust got something from it, didn't just give, it also got